Okay, so the class today, we're going to talk about the web ontology language, and we're going to focus on how the web ontology language is defined. So the last time we spoke in the last two classes, starting with RDFS and then with OWL, talking about the logic part of the semantic web, where we can define these sorts of inferences that allow us to access not just the explicit content of the web, but also the things that can be entailed or implied by the web, the implicit knowledge of the web. For example, in this case, to know that if Ireland, capital Dublin, and if Ireland part of Europe and Ireland capital Dublin, then Dublin is part of Europe, for example. So we're going to continue to talk about OWL and in particular how it's defined. So we saw these examples in the last class to kind of exemplify the use of the different features of OWL. However, they were just examples. So today's topic, we're going to basically try to give a meaning or define the semantics or define what these things actually mean, not just in terms of examples. So the idea would be to capture somehow the main ideas of OWL. I'm not going to get into all of the nitty-gritty detail, for which if you want to know more, you can check out the book that's linked from Cursus, but we're going to give a good approximation, or at least what I think is a good approximation in my own mind. So this class and the next class in particular are somewhat more conceptual, theoretical classes. They're not 100% linked to the labs. You can do the lab of this week and next week based on last week's class. It's enough to just know intuitively what the features mean. So it's sort of maybe more along the lines of their classes more linked to, I guess, the postgraduate aspect of the course. But hopefully you find it interesting, these more conceptual topics in the next two classes. So how do we define OWL? And we're going to get into how do we define knowledge representation? How do we formalize knowledge representation? And we'll get into aspects of computability with respect to representing knowledge about the world in terms of reasoning, what we can do and what we cannot do. So defining OWL, we saw this example in the previous class where we defined the class Godfather as being equivalent to essentially the class with three individuals, Vito, Michael, and Vincent. So how can we formally define what this means? So one idea would be, since we're really mostly interested in what these sorts of definitions entail, right? Godfather, equivalent class, one of Vito, Michael, Vincent. What we're mostly interested in is what these definitions entail. We could think about defining the semantics with rules, right? So we could say, for example, if we have that a class C, which is a variable, is an equivalent class of one of x1 ... xn of several individuals, then we can entail in this case that each of these is of type the class. So in this case, we would define the rules such that Vito would be of type Godfather, Michael type Godfather, and Vincent of type Godfather. And this is sort of what we did for RDFS in a way. We can somehow define the semantics equivalently using rules for RDFS. However, for the more complex OWL standard, this doesn't really work so well. So, okay, we can, in this case, write rules to get certain inferences like this, but it doesn't really capture exactly what it means, right? So if we were to think, for example, now that we have another individual who we know is of type Godfather, what do we know from this? What could we guess about Vito Young? Any ideas? So if Vito Young is of type Godfather, and Godfather is the class with these three people here, then we'd have to figure that Vito Young must be the same as Vito or Michael or Vincent. Somehow must be one of these, must be the same as one of these three individuals here. So, okay, well, we can also, where's that? What we're assuming here is that Vito Young must be the same as Vito, I guess. Sorry, no, this is stated. So we're stating that Vito Young is different from Vincent and is different from Michael. Then we could infer in that case that Vito Young must be the same as Vito, right? So if we know that Vito Young is one of these, and we know that he's not Michael and he's not Vincent, then we must know that he's Vito, right? And this is a perfectly valid inference, a perfectly valid entailment that we should expect to get from these L definitions. So, however, trying to define a rule for this case is very challenging, right? So how do we define a rule for this case? We can, right? We have certain data in RDF and we entail some new fact, which is that Vito Young is the same as Vito. So we could try a rule like this, you know, if C is equivalent to a class of one of all of these individuals and something is of type that class and something is different from everything else in the class, then it's going to be the same as the first element of that class, right? But there's a variety of problems with this rule. So this is valid. This rule is correct. It's exactly the capturing the inference we see here. But here it only captures it if essentially Vito Young is different from all of the others except for the first element of the list. What about all of the other elements of the list? And if we don't have different from, how do we capture an inference, for example, that Vito Young must be the same as one of these people? So in general, it's not a very general way to capture the semantics of what this means here. What if it's not the first element of the list? Okay. How we considered all possible cases like this. And in general, we see that kind of defining rules is a very limited way to handle, especially when there are multiple possibilities, when there's what we call disjunction. So Vito Young is the same as Vito or Michael or Vincent. And when there can be existentials, which means that when we know that something exists, but we don't have a name for it in the knowledge. So essentially, the conclusion here is that although rules would be an intuitive way to define, to axiomatize or build inference mechanisms for OWL, a finite set of rules may not be able to define everything we need for OWL. So if that's the case, how can we begin to formally define what classes mean? So, okay, what we mean by formally define in general, when we talk about mathematics or logic, is we define something in terms of something else that's already defined, right? And the idea here is kind of already implied by the notation that essentially the class is like a set. It's like a set of things, right? And we have notions of equivalence of sets. We have notions of containment of sets and so forth, elements of sets. So maybe we can use set theory here. So the idea would be to use set theory, which is already well defined. And we're going to say that essentially there is a set of individuals, a set of elements or things that we're going to talk about. So like Vito or Michael, Vincent, it could be movies, it could be more abstract concepts like marriages or whatever we want to describe. There's a set of classes as well, like Godfather. So we have somehow these classes that we can name like Godfather, and these represent classes, okay? Classes map to sets of individuals. So we can map somehow Godfather to a set of three individuals, Vito, Michael, and Vincent, right? And it maps to precisely this set, okay? Then we can map names to individuals, like we can map Vito, for example, to the individual Vito. So, and we can map other names to classes, like we can map the Godfather name to a class Godfather, and in that class we can map it to a set of individuals. So this is generally the idea of how we're going to define the semantics. We're just going to define what it means if somehow classes were sets, right? And then it becomes very easy to define one class as the intersection of two other classes or the union of two other classes, because it's almost the equivalent in what we would do in sets. What about properties? The case for sets is pretty straightforward. But in the case of properties, here we have Connie sibling Fredo, and then we say that Fredo sibling Connie. So in this case, how can we begin to formally define what properties mean? It's not just that a property is a set of individuals, it's more that a property refers to a set of pairs of individuals, right? So we could map sibling to, for example, Connie, Fredo, Fredo, Connie, and all such pairs of siblings, right? So when we define the meaning of properties, we already have that there is a set of individuals and classes mapped to sets of individuals, to subsets of those individuals, what we say. There is also a set of properties, like somehow this conceptual notion of sibling, right, which I used the picture for. Properties map to sets of pairs of individuals, like this property here will map to Connie, Fredo. Again, it doesn't map to the terms, right? It's actually mapping to somehow some notion of the people, to the individuals, to what they refer to those terms. So we have property, which is the sort of the general idea of sibling maps to a set of pairs of individuals, and we sort of assume that those individuals are siblings. So names map to individuals, classes, and or properties. So we can have sibling can refer to a property, Connie can refer to an individual, a person, and we can have person that can refer to a class. So we have these three types of things, sort of individuals, classes, and properties. And that's pretty much the basis for the definitions. Any questions so far? We all good? Okay, so we have sets of things. We have subsets of those things called classes, and then we have sets of pairs of those things, which are referred to by properties. Okay, so now we need to somehow use this to build a knowledge representation, a way of defining knowledge representation that can describe the universe. So, okay. So what individuals do we consider? Do we, how do we, somehow choose what individuals we're going to be describing here, especially if we want to have something general enough to describe the universe or beyond. So the simple answer to that is if we want to describe everything, we're going to simply define the universe as a set, right? So essentially we say that the universe is the set of everything. It's you, okay? So it's somehow this abstract set and has all of the things in there that we might want to describe. So that was easy, okay? So we define the universe as a set of everything you. Okay, so what next? So we have a set of everything, whatever things we could conceivably describe, yeah, not necessarily a finite set. This is a very deep message in chat. Yeah, I don't mean you in that sense, but yeah, you are the universe. So define the set as the universe as a set, which is a set of everything, and it could continue on arbitrarily, right? So what next? We have classes and properties. So we can think about classes effectively as being or referring to. I say being and referring to in kind of essentially a class exists in itself. It's not just the subset. It could be like Godfather is a class, you can name it, and then it refers to a subset of you, okay? But maybe that subtlety is not so important right now. And properties refer to sets of pairs from you, okay, as we saw. So in general, this is what we're describing, right? We're just describing set of things. We have classes, which are subsets of those things, and properties, which are sets of pairs of those things. So what about the terms, the vocabulary or the data? What we need to somehow do then is map the terms. For example, we need to map the term Connie to this individual, this particular element of the universe here. So we also need to be able to name or describe things in the universe. So for this, we define some vocabulary, which is the set of identifiers that we can use to identify things in the universe. And then we have triples, which allows us to speak about those things, how they combine or how they relate to the things in the universe. So here V is the set of all the IRIs. And I'm not going to talk about literals and blank notes because we're mostly at a kind of conceptual level. So V times V times V means the set of all triples of IRIs here. And I'm just going to ignore literals and blank notes for simplicity. So we have these triples, which are sets of tuples of three, like three of IRIs. And then we have a graph, and this notation here means the power set of triples. So it means essentially a graph is a set of triples. This is what we're defining here in terms of set theory. So we have a set of IRIs, we have triples, and then we have sets of triples, which are graphs. So this is essentially what we're using. This is essentially what we're using to describe the universe, to describe things in the universe. Okay. So we can name those things, and then we can define relations between them using triples. And then if we combine multiple triples together, we have an RDF graph that describes lots of stuff about the things in the universe. So the last thing then, we have the universe. We have the vocabulary and the triples in the RDF graph, which is sort of the data describing the universe. And then the question is, how do we relate the data to the universe? So for this, we need something called an interpretation. Any questions or doubts or comments? Okay, if not, we have our data. We have the thing we want to describe, which is this universe. And now we need to somehow link the data and the universe. And this is the part that's kind of weird. It's like, how do you actually define, that Connie, for example, the IRI Connie refers to our example.org/Connie. How do you say that refers to this, person or this character in the universe, in the real world, right? So how do you go about doing that? So the short answer is that you kind of cheat, because you don't really care about Connie. You don't really care about that mapping. That mapping is in people's heads. We make that connection, right? That Connie is something that refers to, and you can't really give a machine a way to, well, at least that I know, to say that, somehow this string here in the machine, this Connie, this IRI refers to this person here. So there's no way, at least that I know of doing that. So what we do is we just define it abstractly. So this, again, interpretation, the purpose is to map the data to the universe. So what do we need in the interpretation? We need to map the terms of the data, which is V, the IRIs. We need to map it into somehow the universe, right? So actually not just that, but the interpretation also defines what the universe is. So we have an interpretation of a vocabulary V, which contains 4 elements: the universe, an interpretation for individuals, one for classes, one for properties. So within the interpretation, here we define, okay, as part of the interpretation, the universe, this is the set of everything, whatever we might want to describe. All the things that we might be interested in describing. Next, we have I, which maps a vocabulary term V in V to an element of U. So this is an interpretation of individuals. So this is basically a mapping from Mary to the person Mary, and Fredo to the person Fredo, and so forth. However, we don't actually really care all that much. This could be any element of a set. We don't really care about the people and the awards and the country so much. These are just going to be elements of an abstract set, right? So we say that Mary maps to something in our universe using I. Next, we have C, which maps a vocabulary term in V to a subset of U, right? So essentially, this gives us the interpretation of classes. So if we have an IRI like person, we can map it to a subset of the individuals in our universe, or a godfather, we can map it to a subset of the individuals in our universe. And we also have P, which maps a vocabulary term V to a set of pairs from U. Okay, interpretation of properties. So we have parent maps to these pairs, siblings maps to these pairs, using the same sorts of notions we described earlier. So the great thing is that all of this is super well defined because we're just using essentially set theory. We're just using sets, and okay, we're using mappings as well, but these are all standard elements of the mathematical terminology or formal aspects. Okay, so this allows us to interpret individuals, classes, and properties. So to map terms from the RDF data into the abstract notion of individuals, classes, and properties. So how do we interpret data or graphs and not just terms? This is just interpreting IRIs individually. So for this, we need to speak about models. So if we have an RDF graph that uses a vocabulary, a set of IRIs, so we assume that we have an interpretation of a vocabulary V. So this V doesn't consider anything about triples or anything or an RDF graph. It just works at the level of the vocabulary, a set of IRIs. So how do we define models? So we define that the interpretation I is a model of G if and only if, given a triple, then essentially the individuals S and O of these triples are in the property P. So what this means intuitively is that essentially the triple that we define, for example, if we have P sibling, actually these should be probably lowercase, which is the convention for properties. But if we have P sibling here, and if we assume that this is Fredo and this is Connie here, then this essentially becomes somehow fits a triple that says Fredo sibling Connie. That's what we're effectively saying here. So essentially the interpretation is a model of G if somehow the individual referred to by S and the individual for each triple in the RDF graph, the individual referred to by S and the individual referred to by O are actually a pair for the set of pairs referred to by the property P. So if we have Connie sibling Fredo, then we would expect that the relation referred to by sibling contains the individual referred to by Connie and the individual referred to by Fredo, which is what we define here. Okay, so we map Connie, we map Fredo, and then we check if that pair of things in our universe is in the mapping of the property P. How do we define the semantics of types? So we know that we have this special RDF type term in our knowledge. So we can say that if in our interpretation, the individual referred to by S and the individual referred to by O are in the property, in the relation of the property P, then we can say that the individual of S is in the interpretation of the class O. So if we have that Connie is of type person, if we have that relation, then somehow we map that relation to the class interpretation, so that we say that Connie, the individual referred to as Connie, must be in the class referred to by person. So this is the sort of base thing, right? So, and this then allows us to effectively model an RDF graph as describing sets of things. So describing universe described in set theory. So how do we define the semantics of subclass? We would use something similar to this here, but in this case, what we're going to have is the individual referred to by S, okay, which is sort of the class, the mapping to the class, the like person itself. The individual map referred to by O. If this is in the relation subclass of, then the extension of the class, which is really the subset of individuals it refers to, will be a subset of the the individuals of O. Okay, so if we say, for example, that person is a subclass of animal, I'm not sure if that's controversial or not, but person subclass of animal, then effectively what we say here is that the subset of individuals that person refers to must be a subset of the individuals referred to by animal. How do we define the semantics of subproperty? Anyone want to guess or think about it? So for the RDFS subproperty of what would it mean? Essentially, it becomes something very similar to this. So it's essentially if the properties are in a subproperty of relation, then their pairs, the set of pairs of S of the first property will be a subset of the set of pairs of O of the second property. And we can continue in this way to define the semantics of domain and range. Okay, this is a little bit awkward, but if S is the domain of O, then what we say is that the first element of this relation, here I'm using pi1, which is sort of like relational notation to project the nth element. So the first element of the relation of S is a subset of the extension of the class O, and so forth. So same for range, it's just this time we're going to project the second element from the relation, so the target of the relation, and then we're going to say that that is a subset of the class O, and so forth. So this is RDFS. For out semantics, we just continue in the exact same way. We can just continue adding arbitrary features with well-defined meaning like subclass, subproperty, domain, and range. We can continue inventing other things, so long as we can define them in terms of set theory. We can continue to define other types of semantics in this way. So how do we define the semantics of same as, different from? We say that if S and O are in the same as relation, then the individuals referred to by S and O must be the same. If they're different, then they must be different elements, not equals. So the individual referred to by S is not the same as the individual referred to by O. Inverse properties. So we say that if S and O are inverse properties, then for all XY that are related by the property S, they must be also in the relation. The pair YX must be in the extension of the inverse relation. Okay, so we somehow say these two things are equivalent. XY is in PX, and YX is in PO. These must be equivalent, right? How about transitive properties? We can define something similar then for all X, Y, Z, such that X, Y is in PS and Y, Z is in PS. This implies X, Z is in PS and so forth. How do we define disjoint classes? Disjoint with, we say that the intersections of the extensions of the classes are empty, and so on. So I'm not going to continue on defining all the semantics, but just to give the idea. And the concept is that all of these things are well defined because it's just set theory notation. I guess it's time for a break. So we could take a break until 10:55. Any questions or doubts, or is it kind of making sense or not? Okay, so we saw the main idea of how to define the different features of RDFS and now using set theory and the first order logic of set theory. So these sorts of definitions here. And so on. Okay, so we could imagine defining all of the other features in a similar way based on what we've seen. So we've now defined what essentially somehow these features mean, but what we haven't defined yet is the notion of entailment between different graphs using these semantic features of RDFS and L. So we still need to define that. So a model here, we define a model, which is a mapping of an interpretation to individuals, classes, and properties. And then we defined somehow some of the conditions that models must satisfy in order to be a model of a graph. So a model is any world that an ontology might describe. So it's any sort of abstract universe described in set notation like we saw that might fit the data that we have. So if we have this RDF graph here, we have 1, 2, 3, 4, 5 triples. We have, okay, here kind of cheating. I'm using 2 labels here to indicate 2 triples between Carmela and Michael, one with has child, the other with ancestor of, and then 3 triples between Michael and Mary, has daughter, has child, ancestor of. So the other thing we have here is the definition that ancestor of is of type transitive. Right. So when we take our interpretation of this, we're sort of mapping them to some elements of some set, right? So we can imagine this as being the actual people or characters in the movie, for example. And we're mapping the properties as well to these abstract relations that themselves refer to pairs of individuals. So then the question is this thing here, is this a model of what this graph might describe, this ontology graph might describe? Does it somehow fit the graph? Is it a possible thing that the graph might be these definitions here might be describing? And the answer is no. And the reason why not is because it's missing something, right? If in the real world somehow that we're describing, Carmela is not the ancestor of Mary, then it's not correct to say that ancestor is a transitive property, right? So somehow if in what we're describing, Carmela, this or this individual referred to as Carmela is not an ancestor of this individual referred to as Mary, then somehow this is not something that our graph is describing. It's somehow inconsistent or doesn't fit what we're describing. So is this a model of the ontology? No, since this individual here would need to be in this relation, ancestor referred to by ancestor of with the individual referred to by Mary, okay? So since that's not the case in the real world, if in the real world this didn't hold that Carmela was the ancestor of Mary, then we shouldn't be defining this here. So somehow this is not a possible world that we're describing. So now we would have a model of the ontology for the given semantics. Somehow this configuration of individuals and relations and so forth fits the data or the definitions that we have according to the semantics we've seen. Okay. So how about this case where we say that Mary likes cake? So if we say that Mary likes cake, somehow we have a model, right? And in this model, we have this relation between this individual and this individual according to this relation here. Is this a model of the ontology? So we never said here that Mary likes cake, and there's nothing to entail. We don't even mention the term cake here, right? So the question is, could this graph be describing this sort of world here where this person likes this thing here? In fact, yes. So this is also a model given the open world assumption. So if you remember, we spoke about the open world assumption. We said that we never assume that an RDF graph is a complete description of the world, which means that we don't assume that things that are not stated are false. So in this case, this is fine. It's essentially our ontology or RDF graph can be an incomplete description of the model. So the model might actually contain more things that we don't describe, right? So in this case, that this individual likes this colorful thing here called cake. So a model somehow has to cover everything that the graph describes and everything that it entails, but it can also have more things, right? The graph can be an incomplete description of the model under the open world assumption, which we take here. So in terms of entailment, which is the sort of key notion here, if we think about what we're doing, effectively when we have an empty graph, it's true to say that almost any world is possible, right? It's sort of like when we don't define anything, then anything can be a model of that, right? Because we haven't really started to define anything yet. And as we add axioms, fewer worlds are possible. So we have fewer models for our graph. As we add more data, more definitions, we start ruling out models, right? From the set of all possible models. So it's this sort of idea of a sculpture. Yeah, at the start you have like a block of stone, which is just all of the models. And as you define things, you start chipping away and chipping away at it to reveal more of what you want to describe. So you start with essentially that you can have any model. You can be describing pretty much anything. You could be describing any possible model. And as you add axioms, then you start chipping away and removing models from that and saying that, okay, this can't hold, or if this holds, this must hold. You start adding restrictions about what you might be describing. So how does this fit with the notion of entailment? So we have some definitions here. We have an ontology described as an RDF graph, and the yellow thing here, has daughter subproperty of has child inverse of has parent, subproperty of ancestor of. Ancestor is a transitive property. Carmela has child Michael has daughter Mary. So this entails a bunch of stuff, right? So for example, if Michael has daughter Mary and has daughter is subproperty of has child, then we know Michael has child Mary, right? And if we have Carmela has child Michael and Michael has child Mary and has child is subproperty of ancestor of, then we have Carmela ancestor of Michael, Michael ancestor of Mary, Carmela ancestor of Mary, and so forth, right? So just to take some examples from that, this is not all that it entails, but it's some of the things that it would appear that this ontology entails. So Michael has parent Carmela, Michael has child Mary, Carmela ancestor of Mary. So if we looked at this, we could convince ourselves intuitively that this ontology entails this one here, right? And we use this symbol here to denote entailment. How we define this now in terms of all that we've seen is we say that any model of this ontology O is also a model of this ontology O prime. So if any model of O is a model of O prime, what it says is that the set of models of that of O prime is a superset of the model, is a superset of the models of O. So the models of this ontology here, the entailed ontology, is a superset of the models of O. So again, if we think about it, it's when we're adding axioms, we're removing models because we're saying more and more specific things. So there are fewer possible models for the graph. So if O prime has a superset, has more models, includes the models of this and has potentially more models, then it means that somehow it says less, right? It hasn't removed as much. So this statement here is equivalent to saying that the models of this ontology here is a superset of the models of this ontology here. Or in simpler terms, it just says that essentially this ontology here is entailed by this one if it says nothing new that we didn't already know from the first ontology, right? So now we can define entailment in terms of the models that we've seen. Okay, so any model of O is a model of O prime. This is equivalent to saying that O entails O prime. Okay, so now we've defined the key notion of entailment. So we're kind of all the way there in terms of how to define entailment. And we use this special symbol here for entailment, which is O entails O prime. So now we formally defined the notion of entailment for OWL and for ontologies. So let's have a look and see. In this case, we have this ontology entailment. So we have to see, first of all, we have to ask, is there an entailment? So we have Carmela has child Michael, Michael has child Mary, and Carmela ancestor of Mary. Okay. And then we say Carmela ancestor of Mary. Okay, that seems to be entailed because we have that directly stated here. And then we have Mary likes cake. So, okay, we can see that probably, yeah, there's no way to entail this, right? So Mary likes cake. So this ontology is not entailed by this ontology here. So the question is, does the first ontology entail the second ontology or not? No. We can say no because there are models of O that are not models of O prime, right? So there is a model of O that's not a model of O prime. Effectively, we can take a model of O as something that doesn't correspond to Mary liking cake. So we omit from our model this whole notion that Mary likes cake. We can have models that are here, but they will not be models here. Okay. So this here, for example, is a model of the first ontology, but it's not a model of the second ontology because it doesn't, we don't have anything to indicate that Mary likes cake. So for that reason, somehow, this second ontology here, this is not a model of the second ontology. So therefore, we can't say that all models of this ontology are models of this one, because here we have a counterexample. This is a model of the first ontology, but not of the second ontology. What does that mean? It means that O does not entail O prime. Right? It doesn't satisfy the condition that we saw earlier. So now we can define the notion of ontology entailment in terms of models. Okay, and all of this is based on well-defined in terms of set theory and first-order logic of set theory. So Mary doesn't like cake here, so it's not a model of the first ontology. Any questions or doubts or comments? Okay. Something in the chat? Nope, no questions. Okay. So in terms of all of that we've seen is sort of defining an abstract mathematical way. The first thing when we think about knowledge representation, the first thing is we need to formally define what we're talking about. We need to formally define, in this case, ontologies, what they mean. And what we mean by formally define is define them in terms of some existing formalism. So that we've done. But that doesn't really help us because it doesn't give us an implementation or an algorithm or a way to reason or to decide entailment between things. So given two ontologies, we still don't have an algorithm or some code or something to say, yes, this ontology entails this other ontology. So we've defined this, and on top of these definitions, if given ontologies, we can define certain reasoning tasks, certain things that we might want to accomplish. Without talking about the implementation yet, we can consider certain procedures that we might want to apply over ontologies. The first would be materialization, which is sort of the thing that we actually do in the lab, which is write down all the things entailed by this ontology, right? So we have that has daughters is a property of has child is an asymmetric property inverse of has parents, a property of ancestor of, ancestor is type transitive, Carmela has child Mary, Michael has daughter Mary, Mary a person is equivalent to having exactly two parents that are people. So a person, if you have two parents that are people, then you're a person. If you're a person, you have two parents that are people or elements of person. So we could start to just write down things that are true according to this, that are somehow entailed by this, but not directly stated, like Michael has parent Carmela, because Michael has, because Carmela has child Michael, and has child is the inverse of has parent, and continue writing down true statements. However, when we reach this particular definition here, then we're going to run into problems, right? So it says that every person has two people that are parents, right? So, okay. And we know that Mary is a person. Okay, so what do we know from this? We know that Mary has two parents that are people. And since those parents are people, they must have two parents that are people. And since each of those four grandparents are people, and so forth. So any problems with this? Yes. Essentially, we can just continue writing down things that are true forever because we have these existentials, which we represent as blank notes here. So we know that Mary must have a parent, and that parent must be a person, and Mary has another parent, and that parent must be a person. And parent one has parent one, and so forth. So we can continue this to infinity, right? creating new parents and grandparents and great-grandparents and great-great-grandparents. Now, someone might argue actually that this definition is not true because at some stage this has to stop. There's no infinite chain here of elements, but for the purposes of the example, let's say someone has defined this, which is maybe a reasonable definition, but at some point there's a boundary condition where the parents of the person were not really people, or were not really human, fully human. So yeah, what's the point here? We can't always write down everything that is true because it can be infinite. The entailments can be infinite, right? So, okay, but still we can consider some notion of maybe partial materialization. Maybe, you know, we say, okay, maybe we're not going to materialize the things that just involve two existentials, for example. We'll maybe infer that Mary has a parent one and Mary has parent two, but then we'll kind of stop somehow here. Yeah, or maybe we'll have some sort of, or we'll just omit whatever the materialization for these sorts of definitions that create existentials or whatever, so we can maybe still do a partial materialization, not write down everything that's true, but write down the kind of most important stuff that is true, which is what we're kind of doing in the lab. Okay, so this is one task that we can consider. Not just that, but we could also from this entail the following. We can entail other class definitions, which might also be infinite. So if we know that person is equivalent to the class that has exactly two people that are two parents that are people, then we can say that it's a subclass of those that have at most two parents that are people, or it's a subclass of those that have at most three parents that are people. Somehow we can continue this to infinity. So we can just say that it's a subclass of qualified cardinality n greater than 2 all the way up to infinity on property has parent on class person. So here, for example, this says that a person has at most 3 parents that are people, which is entailed by the fact that it has exactly 2. Okay, we can just continue running this, materializing these definitions, which are entailed until infinity, right? So in some sense, we can't just write down all of the entailments that hold, right? Because these are infinite. So, okay. So that's the first task, and it's still practical to do it, but we're going to have to be a bit selective about what we write down in terms of materialization. Second, this is the sort of thing that we can apply with rules. This is often what we'll do is we'll define certain rules and we'll run those up until we can't find anything new, and we'll leave it at that, and we won't materialize all of the entailments, but at least we'll say we have all the entailments according to these rules that we've defined. So a second task is that of ontology satisfiability, which has a slightly weird name, but essentially the task is just asking, is this ontology consistent? Does it contain any inconsistencies or not? So another way to describe this is, does O have a model? Can it describe a possible world? If it has 0 models, it means that the ontology is unsatisfiable. It means that there's no model that satisfies it. There's no interpretation that satisfies the ontology. It has no model. So this basically means that it's inconsistent, right? So we have an ontology here which says that person is equivalent to having exactly two parents that are people. And first person is a person, okay, is an instance of a person, and an instance of the class of having exactly 2 parents that are apes, okay? So is this ontology satisfiable? Can we have a possible model? Is it inconsistent necessarily? Or is it possible that, to define some model of this ontology? Does it have an inconsistency or not? Any thoughts? Any guesses yet? Or any ideas? Yes or no? So we say that there is a person, first person, there is this individual who is a person. And this individual has 2 parents that are apes. And since it's a person, we say that this individual must also have 2 parents that are people, right? So is that inconsistent? Not necessarily. No, we never said that this individual has only two parents, right? We also never said that person and ape are disjoint. Maybe the two parents, each of the parents is a person and an ape. So does O have any model? Indeed, it does. It has a couple of ways to cheat, even though it might seem that it's a contradiction. First of all, we could just say that each of the parents of this first person that ever existed, we have parent A and parent B, and we say that each of these parents is an ape and a person. And this is somehow then a model of our ontology here. So yes, this ontology is satisfiable. It can describe something because it's consistent, logically consistent. There's no conflict here. If we add that ape is disjoint with person, what happens then? Well, in that case, this previous model doesn't work anymore because we can't have that B is of type person and ape and A is of type person and ape at the same time. That would no longer be allowed. So we remove this kind of model here. So ape disjoint with person. So is there any other kinds of models that we can have for this ontology? And the answer is yes, because we never said that the first person only has two parents. We said it has two parents that are apes and two parents that are people. So we can still have, for example, a first person that has four parents, two of which are apes and two of which are people. Okay, so this is still perfectly satisfiable. No inconsistency here. Everything is very much okay. Okay, so this ontology is still satisfiable. What would we need to add to O to make it unsatisfiable beyond the disjoint with person? Well, we could add what we mentioned, which is that people have at most two parents, which we could define are exactly two parents. So a person subclass of exactly two parents. We could define that all of the parents of a person are people. We could define that first person is an ape. This is kind of a cheaty way to do it, but if we say first person is a person and ape is disjoint with person, that would make the ontology satisfiable. Or we could say that first person is owl nothing, which is a special class in owl that's supposed to be the empty class that contains nothing. So, okay, so there's anything that would make the ontology inconsistent. Then it has no model and then it's unsatisfiable. So an unsatisfiable ontology cannot model any world. It is inconsistent, right? So essentially it means that the world, all of the possible models are going to implode and there's nothing left that it can possibly describe. Just to mention briefly that there is a notion as well of class satisfiability as a task, which asks, can we have an instance of this class and still have a satisfiable ontology? So this is the notion of, is a class properly defined? So sometimes we might define so many restrictions about a class that actually, if you define an instance, it becomes inconsistent. But okay, that's a secondary, it's a different task that's sometimes considered. So here we're focusing on ontology satisfiability, which just asks, is the ontology consistent or not? And we define that in terms of models. Does the ontology have any models or not? We also have entailment checking, which is, does O entail O prime? It's this decision problem of given two ontologies, does one ontology entail the other? So this question we can state it as, are all models of O prime as well, which is how we defined it earlier. So how are we going to implement this, these tasks? So for this, we refer to reasoning as sort of the procedure, the computational way that we're going to try to address these tasks, to implement these tasks. So for example, how are we going to implement, does ontology O entail O prime here? Well, there is one trick we can apply, which is we can ask, is O union not O prime unsatisfiable? And when we say not O prime, we're not negating every claim in the ontology, but rather we're negating the entire ontology. So it's sort of, if you have two claims, if O prime says claim 1 and claim 2, then not here would mean not, using De Morgan's, it would be not A1 or not A2. So it says that something is false in O prime, right? Just to clarify that. But in any case, We can rephrase entailment as so long as we have negation. We can rephrase entailment in terms of satisfiability, right? So we can rephrase this entailment question here. We can rephrase it into the following satisfiability question, where we have the original ontology untouched, and then we negate the second ontology. This is the syntax in OWL for saying that Michael does not have the child Mary. And then we ask, is this satisfiable or not? So somehow if this is unsatisfiable, this is O union not O prime is unsatisfiable if and only if O entails O prime. So these two things become, these two questions become equivalent. Okay, so okay, great. So we can somehow reduce from entailment to satisfiability. So, okay, so now we just need to worry about how do we implement unsatisfiability or satisfiability. So how do we test unsatisfiability then? So Audrey Hepburn has this quote of nothing is impossible, where the word itself says I'm possible, which as computer scientists we can say is factually incorrect. There are things that are impossible. So we can't. One of the things that is impossible is unsatisfiability for OWL. We will never be able to, no matter how good we are at programming or at Java or Python or C or whatever, we will never program an algorithm or program a program to decide unsatisfiability, to decide if an ontology is unsatisfiable or not. How can we claim this? How can I say that it's impossible? So the problem is known to be undecidable. So it means that effectively there does not exist a program for this. Let me see what time it is. Nearly time. Any questions or doubts so far? Okay, so the fact that we can't actually decide satisfiability is very disappointing. It means that somehow there's a limit to what computers can do in terms of reasoning, or in terms of what an algorithm or a Turing machine can do in terms of reasoning. So there's somehow things that are not computable in a sense, or facts or theorems, or there are things that we cannot compute. So to kind of ground it a little bit in a specific example that's relatively not simple, but it's very complex in a way, but one that can be described concisely, is the Collatz conjecture. So there is this program written in Java. Maybe I should change this to Python at some stage, but it accepts a number, and if the number is 1, it finishes. If the number is divisible by 2, it returns itself divided by 2, calling itself divided by 2. And if it's not divisible by 2 and it's not 1, then it multiplies the number by 3 plus 1 and calls the Collatz conjecture again. And then we have something that essentially just calls this from a main method, right? So it accepts an input number, and then it runs this program, and then it prints out something. I don't know why there's a print line there, but okay. So how does this work? For example, it starts with 6, and since 6 is even, it divides it by 2. So it returns 3 in the next call, and then it calls itself on 3. Since 3 is odd, it will multiply n by 3. So 3 times 3 plus 1 is 10. And then since 10 is even, we'll divide by 2, and then it will go up to 16, because 5 times 3 is 15, plus 1 is 16, down 16. And once we have a power of 2, we'll just go 16, since it's even 8, since it's even 4, since it's even 2, since it's even 1, and we finish. And there is an open question in computer science and mathematics in general, which is, does this Java program terminate on all possible inputs? If we give this number if we give this program any number, does it always come to 1? Does it always reach 1? And this is known as the Collatz conjecture, that it always reaches 1. And this has remained unproven. It's unknown whether or not this is the case, which obviously means that for all of the cases we've tried up to very large numbers, it does come down to 1. But essentially, there's as far as I understand it, we're not even close to being able to answer this question somehow. As to whether this terminates in all possible positive inputs or not. I think there's a way to define this for negative inputs, but generally we just consider positive integers. The other thing as well would be, okay, here int is like a 2 to the power of 32. Here I'm considering all integers, not just the things we can represent as ints with Java. So actually in this case, strictly speaking, yes, we know that it terminates because we've tried all the numbers up to the limit of ints. But here, I mean the conceptual program, which considers all possible integers, not just the ints. Here I'm going to stop. So this is an example of something, something that's impossible. Not impossible. Well, it relates to undecidability. I'll have to discuss how it relates to undecidability in the next class. Any questions or comments? Okay, so we'll finish this class on Wednesday. There's not too much left. It might be maybe 15 minutes or so, and then we can start the lab. The lab on Wednesday will just be a continuation of the lab last week. So last week you were defining things using property axioms. This week you'll be defining things in terms of class axioms, and mainly you'll be relying on the previous class for that. So and then in the lab next week you'll be combining both and doing slightly more complex definitions for classes. So this is more of these two classes, this class and the next class, are sort of somehow giving more of a background or theoretical foundation for OWL, not necessarily relevant for the labs that come, but they provide some background knowledge. If there's no questions or comments. Okay, see you guys on Wednesday. Ciao, ciao.